So as opposed to solid state sintering, the presence of a liquid phase allows for densification because diffusion of atoms through the liquid phase is much faster. In fact, most of the materials that are sintered are typically liquid phase sintered. So 70% of all sintered materials, 90% in terms of dollar value. You have faster particle bonding, so that's one advantage of liquid phase sintering. It's sort of like welding or brazing the particles together, okay, by the presence of a lower melting material that can dissolve some of the material and pull them to the solid material and facilitate mass transport. Right? Some of the common systems are tungsten carbide, cobalt, titanium carbide with iron, right? Silicon nitride in the presence of yttria and alumina. A lot of the tool steels and stainless steels can be liquid phase sintered as well. Right? A lot of ceramic glasses are liquid phase sintered. So in liquid phase sintering, the final stage involves dissolving the grains and reprecipitating them, followed by coarsening overall. There are other systems in casting, in composites, in Rio casting, right? Whenever you have semi-solid systems, Thixo molding is one type of example. You can have this type of thing going on. Chocolate is an example of a liquid phase sintered system. So you have these dark particles and these bright coarser particles mixed together, and we'll call the dark blue regions as the pores. So initially you raise the temperature, you have solid state sintering between the light blue particles and also the black and the light blue particles, so the additives and the powders. So the black material is a lower temperature phase, and so at some point it goes into a liquid phase. Right? Capillary forces come into play and are able to pull the material closer together, so pores close more rapidly. In addition, some of the material begins to dissolve into the liquid phase, and you have a dissolution and then reprecipitation to cause grain growth. And finally, you have densification by capillary forces again, and you end up filling the entire region, getting rid of voids. The presence of the liquid phase also has another downside. If this overall collapse to the final density doesn't occur uniformly in 3 dimensions, holding precision down is a big challenge. So tungsten carbide cobalt is an example from this microstructure. So the dark regions are the tungsten carbide, the bright regions are the cobalt, and so tungsten carbide can dissolve in the cobalt as well. And so the overall hardness depends upon the relative proportions of the two materials, and also these grain sizes over here. The toughness also depends upon the amount of the two phases. Higher the amount of cobalt, the higher the toughness. This is the example of a cutting tip that would have that type of a microstructure. Of course, this gold color that is obtained is, for instance, from a coating of titanium nitride to provide sufficient heat dissipation at the cutting surface. Another microstructure that's liquid phase sintered is this tungsten heavy alloy. So these are the tungsten regions, and this typically the iron nickel regions that are lighter phase. And so projectiles is one type of application for this. High density materials can be fully densified. Because tungsten is a refractory material, needs high temperatures to very high temperatures to sinter, and this might be the only way to be able to densify some of these materials at reasonable temperatures. A variant of liquid phase sintering is called the supersolidus liquid phase. Here you have elemental powders, and so that can be relatively coarse, and so these are pre-alloyed powders over here in this case. Okay, and when you begin to heat this material, you above the solidus temperature, so super solidus, you begin to have some liquid phase occurring at the grain boundaries within each particle, and that then percolates out of the system and enables neck growths initially to form, and then overall densification between the particles. There's severe particle rearrangement that can occur after that. Okay. So you use these with pre-alloyed powders, and so this is a strategy to use pre-alloyed powders and densify coarser particles than you might have otherwise. The problem is, because of the presence of the liquid phase and large scale rearrangement of particles, controlling precision is a big challenge for these systems. Here's an example of bronze, so copper and tin alloy. This is a 90-10 bronze with 90 copper and 10% tin. And you begin to see these are the regions where some of the liquid phase is being formed, and so you can then see the neck growth that occurs as a result of that. You can see spots where the liquid phase is beginning to exude within the grains itself. When you look at the overall time scale for liquid phase sintering, solid phase sintering occurs in these long times over here, and the presence of a liquid allows the densification to occur at relatively short time scales. So you have 2 to 3 orders of magnitude increase in rates for densification processes. Now there is an idea of a sintering window. That is, you need time and temperature inputs to densify something. Right? But sometimes if you have too much of anything, it's bad. So for instance, initially as you increase the temperature or you wait for long enough times, you transition from a low density porous material to a higher density material. If you wait for too long or you go to too high temperatures, you have grain growth. In the case of liquid phase sintering, you can have more opportunity for distortion. And so these are some kinds of things. In addition, you could have weight loss, where volatile species begin to evaporate from the material, and so that results in lower densification and lower properties as well. Right? So there is a sweet spot, a time-temperature combination that might work well for each material. So basic information is, you want to control this microstructure coarsening, this grain growth, because you can have property loss. Large grain sizes are good for high temperature creep resistance. It's great for magnetic properties, but it's typically bad for most of the structural properties. Right? The Hall-Petch relation, for instance, gives an idea of how properties might change as a function of the grain size. So grain growth lowers strength. So you don't want too much time at the sintering temperature. You don't want too high a sintering temperature. Right? So materials can be over sintered. They fall outside that sweet spot. Right? And so you want to make sure that you understand for a given material how that sweet spot for sintering emerges. As shown in this equation, G0 being the initial grain size, small t being the time, capital T being the temperature, you have a grain growth that depends on time and temperature. And it's a strong function of T, the time. Okay. Of course, these kind of grain growth kinetics are applicable to dense materials too. But given that you have to apply time and temperature to sinter powders, these are competing requirements that come into place.